Okay, so in this video, we're going to talk about the subspace of magic squares, and our goal is to find the dimension of this subspace. So first, let's define what a 3 by 3 magic square is, and it's easier to do it by showing an example. So if you have the square formed by the numbers 4, 9, 2, 3, 5, 7, 8, 1, 6, the sum at each row is 15. For each column, it's also 15. And for both diagonals, you also get 15. So when you have this property where the sum of all the rows and every column and both diagonals, if all of these are the same, then it's a magic square. So you could think of the set of 3 by 3 matrices with real coefficients, but I think we prefer rational coefficients, so let's deal with rationals, such that A is a magic square. Let's consider this set, and let's show that it's a subspace of the 3 by 3 matrices. So what we're going to do is we're going to show S is a subspace of M33Q, although you could change this Q for an R if you prefer the real numbers, or for C if you prefer complex numbers. And then the next step we're going to do is we're going to find the dimension of it. And we're also going to produce a basis. So let's first prove that S is a subspace. Okay, so suppose I'm going to define, what's a nice name? Let's say R of a matrix be the sum of its first row. Now, if A is a magic square, then the sum of its first row is the same as the sum of every other row and every column and every diagonal. So in some sense, if A and B are in S, with R of A equals little a and R of B equals little b, what I'm saying is that capital A is a magic square where every row, every column, every diagonal adds up to A, lowercase a, and B is a magic square where every row, every column, every diagonal adds up to lowercase b. So if you add these two matrices, then the sum of the first row is going to be A plus B. The sum of the second row will also be A plus B, the sum of that. So in other words, because all of these things are invariant, you get that the sum of these two matrices is also a magic square, and it's a magic square where the sum of the rows is just the sum of the rows of the first matrix and the second matrix. Now if you let alpha be any rational, so this will be our scalar. You can change this Q to R or C if you prefer dealing in another field. So alpha will be our scalar, and alpha will not be 0. If you scale a matrix by alpha, then every element is scaled by that same thing. So if you consider the sum of a particular row, because everything was scaled, it's just going to be the sum of the row of the original matrix times this scalar factor. So in other words, alpha times A is in this subspace, and the 0 matrix is also in the subspace because every row, every column, and every diagonal adds up to 0. So we can conclude S is a subspace. Okay. So now the next step is trying to figure out what its dimension. So what we're going to do is we're going to imagine a arbitrary matrix, and we're going to suppose that the sum of the row is k. So it creates the following equation. Set of equations. A plus B plus C is k. D plus E plus F is k. G plus H plus I is k. So these are the three rows. The three columns will be A plus D plus G, B plus E plus H, C plus F plus I, A plus E plus I, C plus E plus G. So we have this 8 sets of equations because there's 3 rows, 3 columns, 2 diagonals. And from here we can create the following matrix. So all the way from here. So let's see. So we have 1, 1, 1. So I guess A, B, C, D, E, F, G, H, I. So we have 0, 0, 0, 0, 0, 0, and then K. Then we have 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1. And then we have 1, 0, 0, 1, 0, 0, 1, 0, 0. And then 0, 1, 0, 0, 1, 0, 0, 1, 0. 0, 0, 1, 0, 0, 1, 0, 0, 1. Then now we have to do the diagonals. So we get this extended matrix, and we want to solve it. And we're going to keep k as a variable. So we're going to do row reduction. And we get the following matrix. From here, we can see that the solutions. So the set of solutions for A, B, C, D, E, F, G, H, I are the following. So A has to be 2k over 3 minus I. B is 2k over 3 minus H. C is negative k over 3 plus I plus H. D is negative 2k over 3 plus H plus 2I. E is k over 3. F is 4k over 3 minus H minus 2I. And then we have G is k minus H minus I. H is H, I is I. So we're left with the following solution set that looks like this. So we have 2/3, 2/3, negative 1/3, negative 2/3, 1/3, 4/3, 1, 0, 0. So all of this multiplied by k. And then we see which ones we multiply by H. It'll be 0, negative 1, 1, 1, 0, negative 1, negative 1, 1, 0. And then we have negative 1, 0, 1, 2, 0, negative 2, negative 1, 0, 1. And then k, h, and I are any rationals. So this means that the dimension of S is 3. And then if we want the basis, what we do is we just grab these these vectors and we create the following nice bases. I'm going to multiply the left vector by 3 just to make it prettier, just so that it's all integers. So we have 2, 2, -1, -2, 1, 4, 3, 0, 0. And then in the middle one we have 0, -1, 1, 1, 0, -1, -1, 1, 0. And the third one is -1, 0, 1, 2, 0, -2, -1, 0, 1. So these three matrices are linearly independent because, well, we could just calculate the row-reduced echelon form, but that's already up here, and we can see that you would get the identity. And all of them are magic squares. The first one, every row adds up to 3, every column adds up to 3, and the two diagonals add up to 3. The second matrix, every row and column adds up to 0, and the third matrix, every row and column adds up to 0 as well. We can create all magic squares by considering the span of these three. All right, that's it for this video.